Okay, welcome back. So now we want to see, can we come up with a procedure like this, and then to reduce the output alphabet of these channels that we create step by step, so to keep the computational effort small and still not suffer too much loss. The idea will be the following. So we're given a channel. W. In fact, maybe let me first say a few words about this. Given a channel W, there is a symmetric channel WS, which in fact preserves the everything. Okay, so preserves mutual information and Bhattacharya parameter, and in fact somewhat more. Let me state this thing a bit more differently. Forget about this. Actually, okay. Suppose we're given a channel W. Okay. Channel W, like this. X and Y. Okay. W. I'll construct a new channel. Okay. I'll call this thing to be the channel, let's say, W sub S, S for symmetric. Okay. As follows. It'll be the following. The channel W is here. The input X to this WS is going to be here. I will corrupt this X by a uniform coin flip. Okay, I'll put here a, let's say U. Okay, so U is going to be it's a Bernoulli-Hoff coin flip, independent of X. Okay, so I'll feed this guy to W. At this moment, you realize the following thing. The thing that you're feeding to the channel W has nothing to do with X anymore, because I corrupted it with a fair coin flip. Regardless of choosing X as 0 or 1, the distribution of this guy here is the same. Okay. So if I do this one, and then call this one my WS, this is completely crazy because I've destroyed all information in this thing. Because of this, I'll give this U to the output. Okay. So the receiver is going to observe both U and the original channel output Y. Okay. All right. This box that I drew here will call to be the channel WS. Okay. Now, the nice thing about WS is the following. First of all, this WS is symmetric. Okay. Let me actually define what I mean by symmetry. So now, maybe let me just start with a couple of examples. Take a look at the binary erasure channel. Okay. Now, this channel has the following property. It looks symmetric. If I replace the 1 with a 0, okay, this channel looks exactly the same if I also replace at the output the 1 with a 0 and leave question mark alone. Okay. So this BEC looks symmetric. Okay. The binary symmetric channel also looks symmetric. So this is, if I swap the labels 0 and the 1 on this channel, okay, if I also swap the labels exactly at the output, you get exactly the same channel back. Okay? So symmetry, I'll define the following way. A channel W symmetric if there exists a permutation pi of the outputs, okay, which is self-inverse. This swapping, if you swap again, you get back with pi inverse is equal to pi. So I apply the permutation twice, you get the where you started from back, such that the W of y given 0 is the same as the W of the pi of y given 1. Okay? So the so if you swap the 0 and the 1, and if you replace the y by the pi y's, you get exactly the same channel back. Okay? Right. So this means symmetry. Okay? Now the symmetry is nice because it is preserved under polarization. If you start with a symmetric channel, the channels W plus and W minus are also going to be symmetric. Easy to check. Okay, just we apply this pi to both the y1 and the y2 at the output of the channels, and then you will see that it is done. Okay. All right. Okay. So now the claim is that if you start with an asymmetric channel, or even a symmetric one, when you do this operation to it, it will be symmetric. Okay. Then let's see why. Okay. So this channel WS. Note that WS of y comma u given the x. So this WS has two outputs, the y here and the u there. Condition on s is equal to, well, no matter what x you send, the u is going to be a coin flip. So we get half for the u. Okay? And then depending on which coin flip we got, we're going to send across the channel to obtain the y x XOR u. Okay. So now let's see. In fact, so for example, the WS of y comma 0 of 0 is half of W of y given 0. WS y given 1 of 0, half WS of y given 1. WS of y given 0 given 1 is half W of y given 1. WS of y and y given 1 is half of W of y given 0. Okay. So now we should now identify, I claim that this channel is symmetric, so I better demonstrate to you what the permutation is. Okay. So these are the outputs of W under the 0 distribution, under the 1 distribution. Okay. They should be the same if I apply the permutation. Okay. So the permutation is then the following. So pi of the y given 0 is y1, okay, and the pi of the applied to y and 1 is y and 0, right? If I do this permutation, you see that the W of a certain channel output given 0 is the same as the permutation of this given 1. These two numbers are the same. These two are equal. And these two are equal. Essentially, you're swapping, if you swap y1 with y0 at the output, and y0 with y1 at the output. Okay. Sorry. If you swap both. If you swap the y1s with the y0s, and at input you swap the 0 and the 1, you get the same channel back. So it's WS is symmetric. Okay. Secondly, the symmetry operation that we have described here, going from W to WS, this thing commutes with polarization. Okay. So it's easy to check. If you take WS and you symmetrize it, you start with W, you compute a W plus, and then you take the symmetric version of this. This is the same as taking the symmetrized version of W and polarizing it. Okay? I say equivalent because they're not exactly the same, because you have to merge a few of the outputs to realize that these aren't the same thing. And similarly, W minus symmetric is the same as W symmetric minus. Okay? So the polar operations and the symmetry operation, they are commutative. So which one you apply first and which one you apply second is irrelevant. You can symmetrize first and then polarize, or you polarize and then symmetrize. They're the same. Okay? Not too difficult to check. It's an exercise. Okay? Secondly, it's also easy to check that if you compute the I of WS, that's the same as IW. The symmetry operation neither destroys nor increases nor creates mutual information. Also easy to check. I guess maybe I should. If you take a look at the mutual information between the input to the symmetric channels, we had X, U, W, Y, and U like this. You need to compute the mutual information between the X and the YU when when X is equal to be 0 or 1. That's by this mutual IWS means that you use the channel WS with a uniform distribution. So you write this guy as being the I of the X and U. This is 0 because the U is chosen independently of the X. And then you have here I of the X and the Y conditional on U. Okay. But since you have conditional, you can, for example, this is the same as the I of the XU and Y conditional on U. Okay. Because the U is already given to you, you can use the U in wherever you want to. Okay, it's not going to change the value of the mutual information. And then you can check that in this particular case, the channel input X plus U to the channel W and the output Y is independent of U. That there's no dependence between these two things. So you can drop the U. This is equal to I of the X plus U, which is being fed to the W channel and the Y, and this is the definition of IW, the mutual information between the input and the output of the W channels when the input has uniform distribution. Okay. All right. Good. Okay. So this is IWS. Similarly, you can check that the Z of WS is the same as ZW. So but the Cherry parameter is also remains unchanged with under the symmetrization operation. Also easy to check. We just write down what is the. We started here with this. Okay. These ones. You multiply the this and that. You sum and so forth. You get the fact that it's the same, but the Cherry parameter computing for the channel W at the end. Okay. So easy computation. Okay. So this is nice because of the following. I can essentially work only with symmetric channels, okay, and then polarize them, and then obtain the good indices. The good indices for the symmetric one are exactly the same as the good indices of the original channel. Okay, but there's a benefit to this symmetrization, which will help us in figuring out this degradation process will be easier for doing symmetric channels than for arbitrary channels. Okay. And the symmetrization does not expand the output alphabet by much. Okay, so the symmetrized version channel only doubles the output alphabets. Okay, that's not a big deal. What I want to do is the following thing. So we're given a channel. Given a symmetric channel W. And I can assume this because if I wasn't given a symmetric channel, I can symmetrize it first and consider that as being the given channel. Do the following things. Okay. Plot the following graph. On the horizontal axis, I'm going to have the all possible outputs of this channel Y. On the vertical axis, I'm going to write what is the value of the entropy of Y, entropy of the input, conditional on the fact that the channel output happens to be little y. Okay. Suppose here are the possible values of this y. Of course, all these values are between 0 and 1. This is a binary entropy. It's the entropy of a binary random variable, so it's never more than 1. Okay. Maybe this one is like that. This is like this. Okay. This is here. Maybe this is the same. Maybe this is big. Okay, suppose you obtain these values here. Okay. Do the following things. Divide this axis into, quantize this vertical axis, okay, as let's say to k levels. It's a uniform quantization. Okay, so I divide them into 1 over k's. Okay, so k quantization intervals of length 1 over k. Divide this vertical axis into 1 over k size intervals, okay, and then see I'm terribly sorry, this is getting to be boring. Okay. So do this, okay, and then now I should have taken a few intervals so I can actually see what is happening. And then to group the y's together, which fall into the same height. Okay, so the height of this thing falls in the same thing. Group these y's all together. Okay, so and then consider the let's suppose script yk. All these y's such that the h of the x given y is equal to k is in the interval, that's y sub, okay, but y sub, let's say, ym is between m over k to this. Okay, so m going from 1 up to k. Okay. Do that. Okay. So then you have classified all these y's into some things. Okay. Actually, let me do one more thing, because about this y's, there's two kinds of information. What is the entropy of the x, and also which of the x's is more likely? Is it 0 or is it 1? Okay. So let me put here also a binary symbol here, b. Okay. This is to say that the y's for which the probability of the x given probability x is equal to b given y is equal to y is bigger than probability that the x is equal to the complement given y is equal to y. So I measure two things about the y. Is this y, under this y, is 0 more likely than the 1? Okay, yes, no. Okay, that's a binary decision indicated by B. Okay, and also under this Y, what is the uncertainty about the X, given that I would have decided 0 or 1? How confident would I be? Okay, that if entropy is close to 0, I'll be very confident. If entropy is close to 1, I'll be very unconfident. Okay, all right. And now, simply, your processor is to simply output MB. So, okay, so now we have the X, W, Y, and here the M comma B, that's for which the Y falls into. Okay, so the index MB for which Y is an element of the script Y MB. Okay, so the processing tells me, I won't tell you which Y that the channel could produce. I'll tell you only the index M and the B that this particular Y fell into. Okay. So the first observation is that the number of possible outputs after this processing is only 2 times k. Okay, so this object here, that's the processed output, has size only 2 times k. This MB takes only 2k values. Okay. And secondly, it is not difficult to show that since you quantize the entropy into 1 over k levels, the mutual information that you suffer by doing this is at most 1 over k. Okay, because these entropies are quantized to only 1 over k levels. At the end, the computation, if I call this the Z, the output of this processor, the channel, and this whole channel is V. Okay. So the channel V, okay, the mutual information between X and the Z is of course smaller than the mutual between X and the Y, because you have degraded this one, but it's not that much smaller. Okay, so the interesting part is this one here. It is the I of xy minus 1 over k. Okay, so you have suffered at most a loss of 1 over k by doing this processing, and at the same time you have kept the output alphabet size of the process channel to be at most 2k. Okay, so, and secondly, the procedure is not particularly difficult. Okay, so it's you just compute k numbers and you're done. Or sorry, y numbers and you're done. You essentially go through each of these outputs one by one, and then you ask yourself, what is the conditional entropy of x given this particular y, and so forth. Okay, so if you start with a channel with already small output alphabets, you can compute this thing like that, and so forth. So let me call this procedure, this degradation procedure to k levels. So my delta is 1 over k. Okay? So remember, in this previous lecture, we worried about making sure that the mutual information loss that we suffer in each degradation step is at most delta. So our delta is 1 over k. That's the most amount of mutual information loss we create by our degradation procedure. So our degradation procedure has the following properties. So this degradation procedure has the following properties. That this I of the V is not too big, is not too small, you haven't lost too much. The output cardinality is at most 2 over delta, okay, with delta being 1 over k. Okay, and if you start from a W whose the computation of V. How do I find out what this V is? Okay. Requires order of the output alphabet of W steps. Okay. You just have to go over the output W one by one, make a few computations for each, and then you're done. Okay. This is how many steps you require. So good. Yes, sir. So it will turn out that V is already symmetric. So if you start with a symmetric W, the V that you create is also going to be symmetric. So you don't need to worry about symmetrizing V anymore. You start with a symmetric V, symmetric W. So you're given a W at the beginning. You symmetrize the W. You do this, and the symmetry is preserved under all these operations. Okay. So now what is nice is then the following thing. So now our procedure to figure out what's happening is this. So you take the W, okay. You transform this into a V. Okay. Maybe W already had too big of an alphabet, so you bring it down to something with 2 over delta outputs. Okay. And then you go to V plus and V minus. Maybe I should call this thing something else. Hold on. Let me call this thing W hat. Okay. This is the degraded version. So W hat or any channel. Okay. So if I put here a not W but a generic P, channel P, the P hat is obtained from P by this procedure. Okay. And then I take the plus of this W hat and the minus of this W hat. So you see, this computation takes order of the output of W steps. This computation takes, to compute the plus channel from the given channel, takes only in the order of the square of the output size elements. This procedure takes computationally only about 1 over delta squared operations to go from a channel, the given alphabet, to its plus or the minus takes that much time. So this also the same. Okay. From this, we go to the hat of the thing that I just created. Maybe I made the alphabet to be very big. I reduce it back. Okay. All right. And I do the same thing again here. Okay. And then I take the plus and the minus of now this object here. Okay. This thing again takes this much steps. This thing takes even less steps than that, order of 1 over delta steps, and so forth. Okay. So end of the day, okay, if I go over here, I don't want to even write down the combinations of the pluses and the hats and so on and so forth. So plus hat, plus hat, plus hat, plus hat, okay, like this. And then the minus hat, minus hat, minus hat, like this, with a growing number of hats and the minus signs. We end up with this. So total computation required here is in the order of to find the tree, to realize the tree to depth I, okay, is the following. The number of nodes in this tree is 2 to the I times 2, because you have 2 to the I nodes here, 2 to the I over 2 I minus 1 nodes here, the geometric sum. You sum it, you get a number which is twice 2 to the I, maybe minus 1, but okay. Minus 1 among friends is nothing. Order of 1 over delta squared. 1 over delta. Yes. Because 1 over delta is the order of the output alphabet size. And to to go to W plus, you have to construct Y1, Y2s and all these things. So you have to go through square of the number of channel outputs. So if this channel had, this computation here, if this channel has about 1 over delta, it's 2 over delta outputs, to compute this one will require square of that. There's a factor of 4 and so on, but I'm ignoring all these constant factors there. So that I requires then times about this much computation, forget the factors of 2. Order of this many computations is sufficient to compute all this tree. Okay, all right. And remember, what we had to do was to make sure that this delta is chosen to be more than 1 over I. To be, no, not more than, less than 1 over I was necessary because of the bound that we had in the previous thing. So we also need to choose, recall, choose delta to be much less than 1 over I to ensure that we estimate a approximately 1 fraction of good channels accurately. So, for example, we could take take then delta is equal to, I don't know, let's say 1 over I to the 10. Okay, I'm being generous. Okay, so it is much less than 1 over I. Okay. Then this will make then the computation will take order of 2 to the I times I to the 20 steps. But this is equal to n times log n to the power 20. Okay, that's the n being the block length of the code that you have. So what you have is, we could have made this constant to be, I could have chosen this, instead of 10, I could have picked 1.01. Okay, then this would have made this thing be 2.02. Okay. So essentially then n times polylog of n computations is sufficient. And this is not big. Okay, so you can do this thing offline. Okay, so essentially the construction of the polar codes also does not take much more than n log n amount of time either. We didn't need that. I mean, this could have been n squared. Okay, it wouldn't have killed us. Okay, but or maybe it would have, depending on what the n is. You may not want n squared, but as long as you have n times some reasonably small polynomial in the n, it is fine. And indeed, these things are I'm being very conservative. Okay, because in fact, when you actually do this process, okay, when you try to implement this procedure, it seems like taking the delta to be a fixed number such as 1 over 100, okay, it seems to work very well. Okay, so you don't need to make this delta change with the I, the number of levels. Doesn't seem to be necessary. So experimental things suggest that once you pick the delta to be like 1 over 100 or something, you essentially miss none of the good channels, and the channels that and the approximation that you make in the mutual information of the channels is essentially negligible too. So you don't really need to do need to be too concerned about this. So essentially, this will bring the, if you actually be taking delta to be a constant works, then this becomes linear in the end. Okay, because the delta is a constant. Just the construction takes linear time in the block length. But to make sure that we are guaranteed to know something, all we need is to make sure that it is n times log squared log cube of n is perfectly sufficient to make to theoretically guarantee that this construction is going to find almost all the good channels and estimate them almost with perfect accuracy. Okay. All right.
At the end of this algorithm,
yeah.
At each stage we group the channels into quantized sets.
The channel outputs into quantized sets. Yes. Yes.
If find out that a particular set is good,
Yes.
all channels in a particular set are going to be good.
So I'm not grouping channels together. This procedure says to, you have a channel, it has a big output alphabet. For example, suppose we started with, suppose my delta is 1 over 100. Okay? So at some moment in this procedure, I'm going to have a channel with 200 output alphabet size. That I'm considering to be okay. When I do the plus version of this channel, I'll end up with a channel whose output alphabet size is 200 squared times 2, which is 80,000. Okay. I'll take a look at 80,000 possible channel outputs, so this W plus channel that I just created, and I'll reduce it back to, again, 200 outputs only. Okay. So I'm not touching the groups of channels. I quantize the outputs of each individual channel I encounter in this tree process. So it's not like I'm grouping the channels, I'm only grouping the channel outputs. And then I continue with, from this new reduced channel, I'll continue to polarizing it that way. Okay? So there's no grouping of channels, there's only grouping of channel outputs to take a channel and make it into a degraded channel. This ensures that the bad channels never become good, because if they did, I might identify an actual bad channel to be a good channel. Degradation ensures that whatever channels I say are good, at the end of my approximation, the original one was in fact good. So that's the one that you're really using. Okay. So our codes are not are designed conservatively.
Can you also decode the message bits using this reduced code?
Okay. Good question. This is unclear. So this has to do with you have a actual channel W, and then you try to decode it with based on the statistics of a different channel V. Okay. So that kind of problem has been looked at by one of my former PhD students, Mina Alsan. Okay. So she did some work on that, and she has certain results on this procedure. So it's a difficult problem in general. So if you design a polar code and a corresponding decoder based on some channel that you have in mind, but if the actual channel that you use is different than the one that you started from, how will you do is still somewhat open. But it's an important question. It seems to work fine. I mean, the experimental study suggests all is well. If you have a V and W are close to each other, fine. Okay, but theoretical results are tough. Yes, sir.
This lecture towards the end, you had chosen delta equal to 1 over I.
Yes. Oh, I only wanted to make sure it is less than 1 over I. So all we had to ensure was that to get this, okay, that would have given us here, instead of 20, given us 4, okay. But I could have chosen it to be instead of 2. Sorry?
That was just a choice.
Just a choice. Yeah, exactly. So, and the reason here was that remember that the average loss that we suffered at the ith level was I times delta. I want to make sure this I times delta is small. So only thing I need to ensure is that this average loss is small. The smaller you can make it, the more accurate you are estimating these channels. So you want to make this I times delta to be close to 0. But if you make it too close to 0, then your delta is very small, so your computation effort blows up. You need to find some trade-off between how accurate you want to be and how much computation can you afford. But from what Alex Vardy and Ido Tal were experimentally studying was that taking, I think, delta in like 1 over 64 or 1 over 128 was giving excellent results, even for block lengths which were very big. So it seems like you don't need to make delta to be as small as we propose here. So the one thing to read is, of course, Erdal's original paper. So one should read. Here's a paper in the Information Theory Transactions. I think must be 2009, I suspect. Okay, which is the first paper. And the title starts with channel polarization. I think something called a method to approach channel capacity, or method to achieve channel capacity. And that is sort of the paper to read. Okay. Now one can also read from a point of view of having reference material read in them, one can take a look at the introductory chapters of a couple of PhD theses, one by Satish Korada, at EPFL. So I think if you just type EPFL PhD thesis Korada, it'll come up. Okay, it should be publicly available as a PDF file. And in his first couple of chapters, he goes through a lot of this introductory material in nice, let me say this, nicely structured way. So he has a unified treatment which he's giving. He's also pointing to other problems that can be solved by polar codes. Okay, it's a very nice thesis. Similarly, there's a thesis of my own PhD student, Eren. Okay. He also has a very nice description as to what is going on with reference material behind them. These are theses which are, of course, necessarily more recent than Erdal's paper because they were written after Erdal taught about polarization. Eren has also as something in the foundations and trends. By now publishers. Same. And then this is a tutorial, I think. On polar codes. I'm not sure what the title is, honestly. It may not be called Tutorial on Polar Codes, but it has the name polar in it, obviously. Okay. So one can take a look at Eren's material. So these will at least give you good pointers to the rest of the literature. Okay. So one could start from these and then expand as to what you want to read. But at least the material that we covered here, they will be covered in some form or the other in these things. Okay. It may not be the same form because I think that the proof that the polarization does happen without the speed and so forth, I think that the way that we did it here is, I think, simpler than the ways that are presented here because they immediately go into these martingales and so on and so forth immediately, whereas we did this thing in a somewhat elementary way. We end up having to use martingales because I had to use the fact that this Z process is a convergent process that goes to 0 sometimes. Okay, so I need to fact that this, if you take a look at how we did this, I use the fact that the Z will remain below some value forever once it gets below, so that this V process that we were having was more than 100 from some point forever. Our original proof does not say that, but the martingale proof does. So I need to use the martingale proof to show that the speed of polarization is what we claim to be. It requires the martingale. So I cannot completely avoid the martingales. If I think of some other way to do this thing in the next few months, I'll start teaching the polar business somewhat differently. But at the moment, if you have to really treat the polar codes correctly, at some moment you have to introduce these martingale processes. It seems artificial. Sorry? Third reference. Same author. So this E is Eren, Sasoglu.
The title of this is Polarization and Polar Codes.
Which one?
Fourth one. The title is Polarization and Polar Codes.
I see.
And it appeared in October 2012. Foundations and Principles, Communication Network.
And polar codes. You said what, 2012?
Yes, October 2012.
Okay.
Foundations and Principles, Communication Network.
Okay. So it's easy to find even if you don't know the title, obviously. So if you could find it in 5 minutes. I see. Okay. Sorry?
October 2012.
Yeah, but I think that Eren is not going to have 1,000 papers published between now and then. So I mean, if you just search for his name, it's not an easy name either. So it's not like you're going to find 17 different thresholders all working on polar code. It's impossible. So Google searches his name with a polar in it. You're going to find some number of his papers. One of them is going to be a tutorial. Okay? As far as tutorial material, I don't really have anything else in mind because there's lots of research material which is published, but there's too many. I mean, if you go to the information theory conferences these days, there will be 3, 4, 5, 6 sessions on polar codes in each of them. So each session contains 4 or 5 papers, so there is a lot of stuff being published. But tutorial material is not that many, and these are actually are very nice ones. So once you read them through, you actually know what is happening. Unless you need to know exactly what is going on this month, then you take a look at the archive and so on to see what is going on. But my philosophy is typically to just read something simple and then think of it about it myself. So can we connect the constructions of these codes with Reed-Muller codes? I would like to answer yes, but it is not so easy. So clearly, you start from the same big matrix. This is the big N by big N matrix, the Hadamard matrix that you have. You take the 1101 matrix, and you raise it to the Hadamard power n, or Hadamard power maybe I. This gets you a 2 to the I by 2 to the A matrix, big N by big N matrix. And then the Hadamard code will select columns or rows depending on how you think of our symbols. If you are using row vectors, it is picking some number of rows of this matrix as being the generator matrix, okay, of the code. And the polar codes are choosing, again, from the same matrix, they're choosing some other rows as being the generator matrix. So they're clearly related to each other. And there are some rows in common, but some rows are not. Okay, so the polar codes are not Reed-Muller codes. Okay, so they're different codes. Nonetheless, they descend from the same grandfather. So I would call this cousins. Okay, they share a parent matrix here. Now, there are ways to interpolate between polar and Reed-Muller codes. Okay, so there's work by Marco Mondelli. Okay. His original, I think, motivation, maybe I'm putting words in his mouth, but maybe it may be false, to essentially try to show that, attempt to show that the Reed-Muller codes achieve capacity of symmetric channels by lifting from the fact that the polar codes achieve a capacity of all symmetric channels, and that somehow you can go from polar codes to Reed-Muller codes in some nice continuous way, sort of without losing too much, etc. Okay? So he had described some procedure as to how to interpolate between polar and Reed-Muller codes, but at least that approach did not show that the polar codes were the Reed-Muller codes were capacity achieving. Nevertheless, him and his advisor Rudy Urbanke, also together with, but independently of, a group in Duke University with Henry Pfister and his students, they were able to show that Reed-Muller codes achieve the capacity for binary erasure channels. Okay, not all binary symmetric channels, but for the particular case of the erasure channel, the Reed-Muller codes are capacity achieving. And this was done in the last maybe year or two or something. There's they wrote a joint paper, which was it's a very nice paper. I would recommend you read that also. But the approach is very different than polar. So in that particular paper, there's nothing polar in it to show that Reed-Muller codes achieve the capacity of the erasure channel. Use a completely different technique, but I think that at least the question was inspired from polar codes. So I'm sorry, I don't know I cannot recall the name of the exact paper here, but
from polar to Reed-Muller codes, a technique to improve finite time.
Okay. Something. Okay, so thank you, Adrish. He's being the Google of the of the group. Well, there should also be some ISIT paper too, I think. But sorry, author is Marco Mondelli, Mondelli, and others. Okay, let me just write his name, and then you can find the others. I'm not trying to be in any sense complete or giving all possible credit due to all possible persons. It's not my goal here. So people might get angry with me, but okay. So there are others who have worked on this topic whom I'm not mentioning, but they have equally good work. Almost anything. I mean, the number of solved things is tiny. So essentially, almost any question you think of about polar codes is going to be unanswered. Yes, the whole topic is essentially from, I mean, less than 10 years old. So the people have wrote about this, but to sort of, but almost many things are open. And by the way, I mean, I should really qualify all these statements as saying I'm not really a coding theorist. Okay, so I came into this business by being an information theorist because these codes are not really codes. Okay, this is you're doing information theory and then disguise it as being coding theory. So I won't know some of the things that a coding theorist would naturally know about these things. So some of the questions that you pose, I may not be able to give correct or precise answers to. So looks like we are almost done. Well, thank you very much for bearing with me for so long and for so many days and so many hours. It's very pleasant to be here. I'd like to thank Adrish again for giving the opportunity to visit here and speak to this distinguished group of students. Thank you very much indeed.